This is a brief tutorial on the information you're going to need to provide for each of your simulations that you want to be set up for the experiments that you're running for your semester project. Uh, as a way to explain the various pieces of information that the global climate model requires, I'm going to use the EdGCM setup simulations form. This is the form that I'll be using to actually enter the information for each of your runs. And I'll just walk through this form and explain a little bit about what each of the sections um, provides for the GCM. And then on the right-hand side, what you see here is a template that we'll be giving you. This is a template you'll be able to fill out so that I can fill out these forms for your simulations. Most of your experiments will include at least one climate change run and a control run. The climate change runs can either be future climate change runs or paleoclimate runs. And I'll say a little bit more about that as I go through the setup simulations form. The first section for the setup simulations is just a general info section. And you'll need to provide a run ID. This is just a short abbreviation description of your simulation. It allows you to have a maximum of 19 characters. You'll need to supply a start year and an end year. This run starts in 1850 and goes to 2100. Um, the uh, the only reason you'll need to supply these start and end dates will be if you're running future climate experiments, because you'll want to start somewhere in the past and run up somewhere into the future. These runs should be no longer than 250 years, and if you can keep them to 150 years, your runs will go faster. For paleoclimate runs, we automatically run those simulations for 100 years. You'll need a project ID here. That project ID would be best if you just have a short abbreviation again of what your project is about. The owner here, which has my name right now, this would be best if you could just come up with a short group name. Then there's a run label. The run label can be a maximum of 60 characters. This is a slightly longer description of each of your simulations. Then there's a comments section here. For your comments section, I'm going to paste in the text from your proposal that you are getting approved by your professor. The next section is an input files section. This is the section in which we define the boundary conditions that are used for the model. Boundary conditions include things like the topography, the vegetation, and a few other things here that you don't need to worry about right now. For your purposes, I mostly need to know whether you're going to run a future climate simulation, in which case you'll be using roughly modern continental configuration, or if you're going to use a paleoclimate simulation. If you use a paleoclimate simulation, you can choose between a snowball Earth configuration. That's the Earth as it was approximately 750 million years ago, or a Cretaceous configuration. That's the Earth at 100 million years ago. The Pliocene, which is a time period of about 3 million years ago, or an Ice Age simulation. The settings that I'll enter here will be appropriate based on which of those time periods you choose. Most of you will probably choose to do future climate simulations, I suspect. The GISS model does allow you to use different ocean models, but for the purposes of a semester project like this, all of the projects will use what's called a mixed layer ocean model. A mixed layer ocean model is a simple ocean model that simply allows the upper surface of the ocean to adjust to climate changes. So you won't need to actually tell me what type of ocean model you want to use. Modern GCMs would use a dynamic ocean, which would simulate the full depth of the ocean, but those simulations take a very long time to run, and so they won't be used for a semester project like this. The diagnostic output, um, uh, although there are choices that can be made here as to what diagnostic output is collected by the GCMs. For this project, you will actually be supplied with a set of, or three data sets of climate variables. They will come in the form of a series of climate variables that are time series for your runs. So for each of the time series, you'll get a global annual average for each climate variable for each year of the run. And then you'll get a series of latitude by height climate variables and another data set that are a series of climate variables that are latitude by longitude. In other words, those are your map variables. And um, and each of these data sets includes, I think, anywhere between 15 and 30 different variables that you'll have available for analysis. The forcings section is where most of your interesting work will need to be done for your proposals. The forcings that are allowed to be set in the GCM are greenhouse gases. There are 5 different greenhouse gases that can be set in the GCM: the carbon dioxide levels, nitrous oxide levels, the methane levels, and 2 types of chlorofluorocarbons. You can either choose, so the values that you first set are like, what is the initial value of each of those greenhouse gases for your simulation. So when the model run is first initiated, it will start up using the values you give at this point. Um, the the option for simulations that are future simulations would be also that you can pick a year, any year after 1850. You can actually choose a year, and that will automatically set the values based on observations for that particular year. So if you picked to start your runs in 1950, the values would be set at the observed 1950 levels. For all paleoclimate runs, runs that are therefore prior to the pre-industrial era, the CFCs are zero. As a matter of fact, CFCs are basically zero prior to World War II. You'll also need to supply a solar luminosity. Again, if you're doing a future climate experiment, the solar luminosity level will just be based on your start year from an observations data set. If you're doing a paleoclimate run, you have the option of using a value that we could provide for that particular time period, or you may actually be doing experiments. You may choose to do experiments in which you're testing the effect of different levels of solar luminosity, in which case you can either provide a solar luminosity in watts per meter squared, or if you want to do something like test the effects of a 2% decrease in solar luminosity, I can calculate the level of solar luminosity based on that kind of information. You will want to keep your changes in solar luminosity well below 10% change, because the model will crash with changes that are larger than plus or minus 10%. The orbital variations, these we'll pretty much leave as they are. This is sort of a modern set of orbital parameters for the Earth. The Ice Age simulations do have a different set of defaults, but that would just, if you're doing an Ice Age simulation, once I know that, these defaults will change. Some of more sophisticated will be simulations that you decide to run that include various trends in the greenhouse gases. And this is a real common type of experiment that people choose to do for their semester projects. For every greenhouse gas, you're allowed to set a trend in that greenhouse gas. Now, the starting value will be, again, based on the value that you gave for the initialization. But there are various ways that you can set the trends for each of the greenhouse gases. You can do something, what's shown here is that each one of the trends is set from a data file. And I'll just pop up an example of what these data files look like. If you want to create a trend in any of the greenhouse gases for your various simulations, what you need to do is you need to create an Excel table where the first column is the year of the run, and any subsequent columns are the level of that greenhouse gas. In this case, this particular project was testing the three different CO2 trends. And so that's why there's three columns here. And so each of these columns then is a trend in the carbon dioxide that changes over the course of this experiment went to the year 2100. And you can see by the end, the simulations all have different CO2 values. So you can do something that is a complex trend just by changing these values in this table. But if you don't want to go to that level of complexity, if you want to do something along the lines of what happens if there's a 1% increase in CO2, you can simply say, I would like a trend in this run that increases the carbon dioxide by 1% per year. And then the CH4 increases by 1% per year, or you do that for each greenhouse gas, and then you can at any for any greenhouse gas, you could also say that you would want it to decrease by a certain amount, or you could have it stay stable. So each greenhouse gas would need to have some form of a description of what the trend would be for that particular greenhouse gas. So as I said, you can just have trends in one greenhouse gas and all the others could stay stable, or you could adjust all of them individually with individual trends. So you can come up with more complex trends. For instance, trends that increase and then decrease, or increase, stay stable, and then decrease, or stay stable and then increase at a later date. But for more complex trends, all you do is you create an Excel table like this with the year in the first column and then a column that represents the value of that particular greenhouse gas and how it changes each year over time till the end of the simulation.